Hello everyone. We're extremely glad to welcome all of you to the monthly colloquium series by CARINAS. And we are very delighted to have Professor Pallavi Bhat as our today's colloquium speaker. Before getting started with the talk, I'll say a few words about this forum, CARINAS. CARINAS currently has more than 300 Indian researchers working in astrophysics and related fields, with 41% within India and 46% who are currently studying or working abroad. And 87% of our members are early career researchers who are in the formative stages of their career. These are the stages in which we start losing women researchers from academia due to various reasons. This forum's goal is to empower these early career women researchers in India and first generation Indian women researchers outside the country through networking, support, mentorship, knowledge sharing, and collaboration whenever it's required. We aim to address gender inequity in a bottom-up approach and create a safe, friendly, and inclusive environment and collaborate with other national and international organizations to amplify our impact. Among our initiatives towards reaching these goals, we have started a newsletter series where we not only focus on the great sciences done by women researchers, but also their life experiences in academia. For example, we already have our two newsletters, and our first and second newsletters captures the experience of several women astronomers and their sciences. And the next edition is going to be launched in June or July with some very exciting content. So stay tuned. And also check out our website, carinas.co.in, for all of these updates. So our second, this kind of initiative is this monthly colloquium series where we already have our quite a few talks by several professors. Now the time for the talk by Pallavi. So I'll pass on the virtual mic to Prakriti to introduce Pallavi.
Thank you, Manami. Warm welcome to everyone, and we are very excited for Pallavi Bhat's talk. Pallavi did her PhD she graduated in 2015 from IUCAA Pune. She stayed for a year in PPPL Princeton, and then she spent a few years, I think 3 years in MIT for her postdoctoral research. And then on her way back, she briefly stayed in UK in the University of Leeds. And then she joined as faculty at ICTS Bangalore. She has strong expertise in turbulent dynamo, magnetic reconnection, and also MRI instability in accretion disks. So generally, she's interested in astrophysical fluid and plasma and all possible applications in astrophysics. Today's talk is on understanding the universe with a magnetic lens. And without further delay, I will request Pallavi to start. Thank you again for giving this talk.
Yeah, thanks, Prakriti and Manami, for also inviting me to give this talk and also the kind introduction. And I'm very happy to, be part of this colloquium series. And it's a really nice thing that you guys are doing with this CARINAS, the super exciting things. So very happy to do this. Well, today's talk is an amalgam of all the works by the various people in my group. So I managed to make a group in the last 3.5-ish years. So we are all doing some interesting work, I think. So I hope you also find it interesting. So I'll give a flavor of all of it, and I will focus on one particular work, which is the application to galaxy clusters. So I'll focus on that in the later part of my talk. Yeah, so the outline is I will first present some observations which will motivate why we want to understand the universe from a magnetic lens. Then I will introduce all these magnetic phenomena that Prakriti mentioned, and alongside some of the work that we have been doing here. Then I will go to the main topic of today, which is looking at how to understand the non-thermal emission in galaxy clusters, which involves particle acceleration and a new mechanism that we are introducing called magnetic reconnection for particle acceleration. Then some of the results, then what do these results from simulations imply, the estimates that we make, and then I'll summarize. Okay, so these next two slides are some of the standard slides I show in my talks. Here are some observations from some of the astrophysical objects that we have. The one that is the closest to us, the sun. So you can see that in these panels, there are these sunspots on top of the sun, which is where magnetic fields are in high concentration. Corresponding to this, this image is this magnetogram, which shows that indeed these sunspots correspond to regions with high concentration of magnetic fields. And then you can actually make this plot, which is this longitudinal magnetic field integrated, the radial magnetic field, which is integrated longitudinally. And this is plotted with respect to time over many, many years. And the very interesting thing that you can see is that there is some kind of pattern that emerges. And this pattern stays for years, and it has a cyclic period associated with it, etc. So this kind of gives you an indication of the fact that there are these magnetic fields in the sun are doing something really dynamic on temporally long scales, and not only temporally but also spatially. So there is this spatio-temporal organization, which is astounding. And so we want to understand what drives this. And then if we go to some of the larger scales, like galaxies, then you also see magnetic fields associated with galaxies. So these are radio contours that you see at 6 centimeter. And then you can see some yellow lines, which show the polarization of the magnetic field associated with the galaxy. And you can see that the alignment of these yellow lines is actually on really large scales, almost on the scale of the spiral arms, indicating that there are these large scale fields. Then again, the question is, where do these large scale fields come from? Going next to a slightly smaller scale, you have, again, you cannot underestimate the importance of magnetic fields in accretion disks, also where they are responsible for many interesting phenomena like jets. So this is the famous image of the black hole of Sagittarius A that came out in 2020 or 2019, and Andrea Ghez won the Nobel Prize for it. And more recently, just in March or February this year, we also got the polarization data, which indicates the magnetic field presence in center of Milky Way and so on. Again, it will be very surprising that even on the scale of galaxy clusters, which are some of the largest objects in the universe, gravitationally bound objects, that you have magnetic fields even on those kind of large scales. And this is the gas associated with this galaxy cluster here, Hydra cluster. And you can see that there are jets emanating, and there is some radio emission associated with it. So again, indicating that there are magnetic fields, etc. So why should we care about these fields, right? So the large part of our universe, the visible universe, is made up of plasmas. So 95% of the universe, the visible universe, is made up of plasmas. So magnetic fields are somewhat ubiquitous, and so it is important that we give them, the consideration that is due, try to understand them. And of course, there is much to be benefited from understanding to make sense of many observations. And also, the interesting thing is that magnetic fields changes the property of the plasma in all of these systems. So it affects all of the interesting dynamics, heating, transport, etc. And it is thought to control star formation, and we can trace perhaps galaxy formation using magnetic fields. And like I said earlier, in accretion disk, it plays a very important role. The cosmic ray propagation is guided by magnetic fields, etc. Then, of course, a very important thing is that all of these radio observations that you see is because of magnetic fields, because there is synchrotron emission that's coming from, these relativistic electrons gyrating around the field. So one wants to understand why do these fields exist in these astrophysical systems and acquire such large scales of coherence, right? That I've been showing in the past slides with all those observations. Now, the most successful paradigm, or the most popular paradigm, is one known as turbulent dynamos to understand the origin of these fields. Before this paradigm came along, a lot of astronomers thought that these fields could be generated in early universe, and then due to what is known as flux freezing associated with magnetic field properties and plasma, you can have a sustenance of these fields over a long period of time. But what others have shown is that if you invariably you will have turbulence in this system, and that turbulence will actually kill these magnetic fields over a period of time. So you will not be able to sustain these primordial magnetic fields if they were the origin of, if early universe was the origin of these magnetic fields. So you need some other mechanism, and thus turbulent dynamos. And what do? They basically convert the kinetic energy of turbulent motions to magnetic energy. So what's happening is that, imagine that this is the magnetic energy spectrum, and this is the wave number. So this is energy against length scales. Okay, so there is some energy that is being injected on some scale. And of course, if you have turbulence, that energy propagates to smaller and smaller scales, and then it dissipates. But along the way, it can actually do very interesting things. Yeah, please do feel free to just unmute your mic and ask questions. I saw a hand, so then I said that. So it can do two things. It can grow fields on either the small scales, the scales smaller than the energy injection scale, or on large scales. And the one that is a generic process is the small scale dynamo. So in the sense that you need very minimal conditions for the small scale dynamo to operate. So one way to physically imagine what is happening is that you have all these magnetic fields on small scales. Then you can take a magnetic flux tube, and basically what turbulence does is to stretch out this magnetic flux tube. And as it stretches out this flux tube, because of magnetic flux conservation, which is a robust property of really highly conducting fluids, then the area goes down, but the magnetic field strength increases. And this can be a very rapid process in turbulent flows. And this can grow the magnetic field exponentially. And that's what is known as the small scale dynamo. But to have large scale dynamo, you need some really special ingredients in this recipe, which I will not really talk about much today. Well, you can ask, where does this turbulence come from in various different astrophysical systems? In the sun, you have convection, which is like all of this boiling plasma, and that's stirring up the fluid and giving rise to turbulent energy. And in galaxies, you have supernovae shaking things up. And in galaxy clusters, you have galaxy mergers, etc., driving the turbulence. So I see like something on the chat. Okay, that's just okay. So please feel, if you don't understand something, please feel free to just interrupt and ask. So I just wanted to show you some of these movies. So this is a small scale dynamo movie, and you can see that the fields are really small initially. The orange corresponds to like weak fields, and then the blue and the yellow are the stronger field regions. And so you can see that initially you really didn't have much field, but over a period of time, due to turbulence, it grows the magnetic field. And but you can see that the scale of the field is remains fairly small throughout the simulation. On the other hand, let's look at what happens with the large scale field. In the large scale dynamo. So again, you have all these small scale motions and small scale fields, but eventually the patches of the small scale field kind of join together to form this large scale field. And this is like really amazing that, you know, there is this large scale field, which is a turbulent magnetic field, but it survives on the, I mean, it basically grows and sustains itself on this large scales. Okay. So this is the kind of small introduction that I wanted to give on dynamos. So let me talk about some of the current work that's being done on these topics. So there are large questions of the large scale, the large question that prevails about dynamo mechanism is basically if they can explain the field strength that we see, and also the dynamical time scales. Are they short enough that you can have the large scale fields that you see in the universe right now? But in particular, in this project, what we are trying to address is, and this project is being done by a PhD student called Mohammad Irshad. He's doing this work about looking at dynamo in collapsing background. So why collapsing background? The idea is that, Prakriti, did you have a question?
So you explained the flux tube stretching for small scale dynamo. Are you about to talk about how the large scale field is generated? Like what is the mechanism? Or
well, I wasn't planning to, but the quick answer.
I mean, briefly.
But yeah, the brief answer is that there is something called helicity. So if you have turbulence in the plasma or the fluid, whatever, then what you need to do is to break the mirror symmetry of this turbulence. So to break the mirror symmetry, you need some particular ingredient like rotation. For example, galaxies have rotation. So that will generate something known as small scale helicity. And that can twist up these magnetic fields. So if you have any topological non-triviality in these magnetic fields, like, you know, helicity, that seems to give rise to large-scale magnetic fields. So this is one small way. Okay. So yeah, so like I was talking about this collapsing background. This is an interesting thing because, you know, in the universe, always you have these gravitationally bound objects which arise due to some kind of collapse, right? So genes instability, etc. So when the star forms, the matter collapses, and as it collapses, it can drag the magnetic fields along with it and do something to it. So this has not been studied too much. There have been some works in the past, but they have not considered this in some full-blown glory that we are doing. So the interesting thing, like I was telling you about flux freezing, right? So the magnetic flux is frozen to the matter. And so as the matter collapses, the magnetic field can grow because, you know, due to the compression. And this growth is something that a lot of people think is responsible for, the magnetic fields that we see in some of these collapsed objects. But I just want to tell you that, this flux freezing is never really sufficient to grow magnetic field to significant proportions. Okay, so you invariably need something like dynamo, which grows fields like exponentially. And so what Irshad has done is this analytical, nice, cute analytical calculation where we take these coordinates which are time dependent because, you are collapsing things. And then you go to the co-moving coordinate and reformulate MHD equations. And if you redefine all these quantities in terms of what are known as super-co-moving variables, you recover back the original equations, or I mean, the equations which look like they are in the original form, and then you can just calculate various things and go back to the lab frame. So then you see that some interesting things emerge. So you can see that if you have only flux freezing, that the magnetic field hardly grows. But if you have the regular dynamo process, then of course you get the straight line indicating that there's exponential growth because this is log axis, right? And then if you do this whole calculation in a collapsing background, then you see that you get something that is even better than an exponential. We call it super exponential. Okay, so this is some really efficient growth of magnetic field. So you may be tempted to think because there is some collapse, there could be some other kind of mechanism which may not grow the magnetic field because the turbulence also increases that can destroy the field, etc. But actually the dynamo really wins big time. So these are some of the nice results that we got. Now let me move on to magnetic reconnection. So this is kind of the opposite of dynamo. In dynamo, you're trying to grow the field, right? But here, this is a process in which the magnetic fields come together, and as they come together and reconnect, magnetic energy gets converted to kinetic energy. So this is kind of the opposite of dynamo in some sense. So what you see over here is there are these reversing field lines coming together. But as the reversing field lines come together, you have a current sheet at their interface. And right at the current sheet, magnetic field lines get destroyed. So actually, the field lines come here and break, and then they reconnect. And the reconnected field line tends to move away from from the current sheet due to Lorentz force, etc. So this is the process of magnetic reconnection, which affects a topological variation in the magnetic field. And this can actually lead to some explosive events. That is, as the fields reconnect, there can be like a burst of energy that comes out of such kind of a thing. So what you're seeing is a steady state reconnection, but you can also have like bursty reconnection leading to what are routinely seen in solar, in the sun, known as flares. There are flares which are like the plasma gets thrown out in a reconnection event. So let me show you like a cartoon of this, what I was just now describing to you. So this is these are magnetic field lines, and now it's undergoing reconnection. And along with the field lines, there's like a lot of plasma which gets thrown out, and then it travels through the solar system and comes towards the Earth. And there, these magnetic field lines reconnect with the field lines of the Earth. And then the plasma goes towards the North Pole and South Pole because that's where the magnetic field concentration is the maximum. And there it interacts with the atmosphere and causes aurorae, etc. So this is some nice thing that's happening because of reconnection. So currently, some of the work that we are doing in ICTS is related to three-dimensionalizing this reconnection. I mean, basically, most of the work that has been done on reconnection has been understood only on 2D planes. Okay, like I showed you the 2D reconnection figure earlier. So it's been understood only in 2D. But it is really important to understand what happens if you generalize things to 3D. And some of this initial preliminary work by Vinay, a PhD student, he's trying to look at what is known as tearing instability, which is one avatar of this magnetic reconnection. So this is the dispersion relation he's looking at. This is the 2D dispersion relation, and the 3D one is down below, telling us basically the 3D reconnection is a bit slower. Okay, but this is not the final word on this problem, because what this stuff is related to low Lundquist numbers. At high Lundquist numbers, something completely different happens that I will tell you about later. But these are some preliminary results at low Lundquist numbers. He's also looking at what happens in the steady state, and that is something that we're looking forward to. Then I will talk about also Shubham's work, which is looking at particle acceleration due to reconnection in galaxy clusters later on. Yeah, so the other work that we recently just submitted is by Shreya and Chandru. This is about decaying turbulence. Now, decaying turbulence occurs in many contexts, particularly also in galaxy clusters in some patches. But particularly, it's interesting in the early universe context, where you think that suppose magnetic field was generated during inflation era, whatever, during early universe, some eras, then how does it evolve over a period of time? This decaying turbulence fits in there, because that considers the non-linear evolution of the magnetic field. And one thing that we have found very recently is that actually the dynamics of such decaying turbulence, if it is especially magnetically dominated, is that there is reconnection happening in it. And in particular, this kind of turbulence is also quasi-two-dimensional in nature because of it being magnetically dominated. So I'm not going to go into any details here. If you are interested, you can ask me later. So now I will briefly talk about magnetorotational instability. It is thought to be very important in accretion disks. Now, the whole problem related to accretion disks was already recognized long ago, that basically you have these very highly luminous objects like quasars, etc., which it seems they're really highly luminous, and there was no mechanism to understand why are they so highly luminous. And then people proposed that there is some accretion of matter happening due to this compact object at the center, and this kind of accretion can be really efficient converter of energy from gravitational energy to radiation, resulting in these very high luminosities. But for the matter to kind of accrete on top of onto the central object, it needs to lose angular momentum. So the mass accretion rate needs to be really high. And if it has to lose angular momentum and fall onto the central object, then you need to have some high viscosity in this system. But as I was telling you before, these plasmas are highly conducting, very low viscosity plasma. So you don't expect this plasma to lose angular momentum fast enough and accrete fast enough onto the central object. So to be able to do this, you need turbulence in the system. And I've been telling you that almost all plasmas and these astrophysical objects are turbulent. But what can cause turbulence in these accretion, during this accretion? So what happens is that you can form an accretion disk because of the usual collapse, and these accretion disks are characterized by Keplerian orbits. Okay, and you find that the fluid, when it is in Keplerian orbits, is actually stable to hydrodynamic instabilities. It's only when you introduced a magnetic field things go unstable. So this was the great success of magnetic fields applied to disks. This was initially formulated by Chandrasekhar in 1960, but nobody really understood its value until Balbus and Hawley reintroduced it in 1992. Where they said that basically if you have magnetic fields in the system, it's unstable to what is known as magnetorotational instability. So the basic idea, I will tell you briefly, is that you have these particles all strung by magnetic fields, and you can think of magnetic fields as some elastic strings. So you can think of these as some spring system, these two masses connected by springs and so on. Okay, so what's happening is that as you go towards the outer radii, the orbital velocity decreases. Okay, so the inner particle is moving faster than the outer particle. So even if things were initially at the same radius, you can give it like a perturbation radially, and then the inner particle will move at a faster rate than the outer one. Right? As it does so, there will be a tension in this spring. Right, and because of this tension, there will be a restoring force, and this restoring force in the case of magnetic field will be simply the Lorentz force, and that acts like a torque to the system, and that will actually further make this inner guy fall inside and the outer guy fall outside because of the conservation of angular momentum, right? And this is like a runaway process, and that's how you get the magnetorotational instability. And yeah, so this instability, then this is like a cartoon thing that I explained, but eventually this becomes, because of the MRI, the system becomes turbulent, and that turbulent viscosity that is affected is enough to give you high mass accretion rates. And so that's why this MRI is super important. So the other thing that is interesting in this system is that because of the turbulence, etc., there will also be dynamo. And in fact, what is interesting is that you cannot sustain this MRI-driven turbulence without actually sustaining some kind of large-scale magnetic field. You really need some kind of large-scale magnetic field to sustain this. And so invariably, you need a dynamo process to make that work. So some of the recent work that we did was to understand this dynamic between, MRI-driven turbulence, angular momentum transport, and mean field dynamo that was done by Tushar Mundal, and we submitted in the last year. So the main results that we uncovered was how these mechanisms operate, because this large-scale dynamo is actually quite different from the classical dynamo that we see in other systems that I just explained to Prakriti some time ago, that you need some helicity. Interestingly, there is no helicity here. Okay, so this system is being driven without helicity, and so that is somewhat surprising. And so that is the work that we did last year. Okay, and the other interesting thing, of course, is that you have jets in these accretion disks, right? And so how do these jets form? So to form jets, one of the most essential ingredients is magnetic fields. So you need to have large-scale fields which then facilitate formation of jet on top of these, the central compact object. So we thought it will be really important to look at GR-MST simulations, because without the GR formulation, it is very difficult to get jets. Okay, so you need to have kermetric, spinning black hole, and only when you have spinning black holes do you get jets. Okay, so this is something that we have only fairly recently started studying. So I'm just kind of showing you some preliminary movie that we got, where we had this magnetic field, and then MRI gives rise to accretion. You can see that it propagates towards the central object, and then eventually you also get these jets. So you can see these outflows, collimated outflows. And what we want to really understand is what is the correlation between the magnetic fields that you generate in disks and that you get in jets. Is there a correlation? Is there a signature associated with it, etc.? Because a lot of these accretion disks have different kind of accretion flows associated with them. So in this particular simulation that I'm showing you, the accretion disk is one that is related to what are known as thick disks. Okay, the standard stuff that I was talking about, where you have Keplerian things, are all related to thin disks. And it's only when you have thick disks that you see these jets. So it's not clear why that is. Why do you get these jets only associated with thick disks and not in thin disks? And what is happening to these magnetic fields, etc. This whole jet formation is like an open question. So that is something that we're looking at. So now let me go on to the main topic. How much time do I have?
15 minutes roughly.
Okay.
That will be like, yeah, we started a bit late, so.
Okay. All right. So here what I'm showing are these images of galaxy clusters. So in these 4 panels, you can see image of galaxy clusters, but in basically radio emission. So you can see some very diffuse radio emission in all of these systems. And this is the famous bullet cluster, and this is the coma cluster. And what you see is really on the whole entire megaparsec scale, right? And so it's interesting that, so obviously there are magnetic fields all over the place. And the question is, how do you get these energetic particles? Because you need to get synchrotron radiation, right? What we are essentially seeing is synchrotron radiation. So how do you get these really energetic particles which are traveling distances of megaparsec scale to not lose energy over that period of time? And because you are seeing this diffuse emission from this whole region of 1 megaparsec scale, right? And I mean, if you were to calculate what is the cooling time associated with it, it is about 10 to the power of 8 years. And then if you were to calculate, okay, so I should kind of show, okay, before I go on to that idea, first let me say that, if you were to look at the luminosity flux density as a function of frequency, which you get from these observations, then that goes like this. That is, if you go to basically higher frequencies, then the flux reduces. But essentially, this is like a power law scaling, because this is log axis. And this alpha tends to be around 1 to 2, or it can be 1 to 3 also, depending on different galaxy clusters. Okay, so this is the kind of spectrum that you get for the radiation. Now, like I was saying, to continue my story, so the particle will lose its energy as it travels through this cluster, right? And the time scale that is associated with this the cooling of this particle is some 10 to the power of 8 years. And you can see, I mean, and we know the galaxy clusters have existed for Hubble time, whatever. So then the question is, how do we understand these diffuse emissions, right? So you need some kind of mechanism that actually perhaps re-accelerates the particles. Even if you were to, primordially, if you were given with some highly energetic particles, they will lose energy as they radiate. So there needs to be some kind of re-acceleration mechanism that sustains them at those energies. So the ones that have been studied very much in the past are shocks and turbulence. So you can have these shocks. There are these processes, acceleration processes known as Fermi 1, Fermi 2. The shocks are associated with Fermi 1, a kind of acceleration mechanism, and turbulence is associated with Fermi 2. Fermi 2 is simpler to understand in the sense that if you have like magnetic inhomogeneities or some clouds, so then these particles are, kind of colliding with these clouds and then gaining energy from that those kind of collisions. And so on, but the Fermi 2 process is not very efficient, known to be not very efficient. Fermi 1, on the other hand, can be efficient, but it really depends on the Mach number of the shocks. And these Mach numbers in galaxy clusters are not really that very large. And so again, it's thought that perhaps these shocks are not a very efficient re-acceleration mechanisms, but this is still like an ongoing thing. And also, the lot of the plasma that we see in these galaxy clusters towards the center is subsonic. It's only when you go towards the outskirts that you get these supersonic plasmas, shocks and so on. So then do you really have enough number of shocks in the center, etc., can be like a question to be asked. So we propose another mechanism known as, which I've talked about already, magnetic reconnection. So this is not something new in the sense that people have used this mechanism to understand particle acceleration in many of these high energy systems, like magnetospheres and jets and so on. I say high energy because the magnetic fields there are super strong. They are really strong fields. So there is this parameter known as sigma. So that's the magnetization parameter, and that is the magnetic field's energy divided by the rest mass energy. So you can think of, so you can see how really high energy plasma it must be for sigma to be of order 1 or more, right? So what they have done is, so this is, these are works from Cironi and Spitkowski in 2015, Wu et al. In 2015, 14 and 15. Here, what you're looking at is particle energy distribution. So this is some sort of PDF versus gamma. Gamma here is Lorentz factor, so that tells you how energetic that particle is. So you can see that this is the time evolution plot. So some initial distribution actually picks up in its tail, and then the particles are getting accelerated over a period of time. And the interesting thing is that if you increase the sigma, the spectrum associated with these particles gets harder and harder. That is, you can get more and more high energy particles, and so on. So what's happening here is that you have this reconnecting fields, right? And there is a current sheet at the center. So like I was telling you before, reconnection comes in many different avatars. So you can have steady state reconnection, you can have something called tearing instability. And in particular, this is known as plasmoid instability. So what's happening is that you have the current sheet in the center, but because of plasmoid instability, the current sheet kind of breaks up into small patches, and it produces these very small islands, and then these islands merge together and form bigger islands and so on. So that is what is happening in this PIC simulation. And as it does so, because at the center you have this current sheet, there is electric field associated with it, and then you also have these magnetic mirrors and so on. So there can be a combination of the electric field accelerating particles and as well as the particles being accelerated due to the magnetic mirrors. So these are some of the processes associated with magnetic reconnection. So what we are proposing is that it should be interesting to explore magnetic reconnection also in the context of galaxy clusters. Of course, the fields in galaxy clusters are not really that strong, right? That would be the first thing that you would think of. The second thing is that the galaxy cluster is non-relativistic plasma. All the stuff that this has been done before is associated with relativistic plasma. All of this is relativistic plasma. So galaxy cluster plasma is non-relativistic. And what about, the strong fields, right? So these are the two things. Now, I have talked about fluctuation dynamo before. And actually, if you want to understand the origin of magnetic fields in galaxy clusters, the most interesting candidate is the fluctuation dynamo. I'm sure Radhika will agree with me, who is probably in the audience. And the fluctuation dynamo, like I've told you before, if you have like flux tube, then you can stretch it out, and you can grow because of that magnetic field increases and so on, right? And the nature of this fluctuation dynamo is that it produces intense magnetic field, but only in very small chota regions. Okay, so it has this intermittent nature in its operation, that it produces really strong fields, but very intermittently in both space and time, right? So you can actually get really strong fields from fluctuation dynamo in small regions, okay? But we really need only some small regions which can become, sites of magnetic reconnection. And the other interesting thing is that because you're kind of stretching out the field, and when you're stretching out the field, you're kind of folding these flux tubes. And when you're folding these flux tubes, you generate naturally sites of magnetic reconnection, because this flux tube is the field in the flux tube is reversing direction at the folds. Okay, so this leads to naturally sites of reconnection. So this is our scenario for getting acceleration due to magnetic reconnection in galaxy clusters. So towards this, what we did is to kind of run particle in cell simulations. And what are these particle in cell simulation? Basically, you have the another property of galaxy cluster is that actually it is highly tenuous hot plasma. That is, the temperature is really high. The temperature is around 10 to the power of 8. I mean, when I was showing you earlier some of these pictures, there was also some X-ray associated with it. So that is because of the thermal nature of the plasma. That is basically the plasma being really hot, 10 to the power of 8, that leads to some soft X-ray. Again, you have both X-rays and radio emission. The radio emission is a non-thermal aspect. Okay. So we actually are dealing with a plasma which is very hot and which is very tenuous, which means that it is actually weakly collisional. It is not, it's almost collisionless, you can say. So for studying such a thing, you have to get down to kinetic plasma level. You cannot study these plasmas with MHD or fluid approximation. Okay, so that's why you do what are known as particle in cell simulations, where you are basically dealing with the particle nature of the plasma. Okay, you can't just do like a fluid approximation. You can do that only if the particles are like colliding with each other like very, very frequently. Okay, so here the idea is that you have all these particles and particles are being pushed due to Lorentz forces due to the fields, and then as the particles move, there is reconfiguration of the nature, the distribution of the charges and currents, and that will modify the field distribution. And so that is done by Maxwell's equations, and then you gather the forces and push particles again. So this is the way in which particle and cell simulations operate, and we have used what is known as WARPX. Okay, so here is what we have done is to study magnetic reconnection in non-relativistic plasma. Okay, and here I show you a site of reconnection. So we look at what happens to these particles as magnetic reconnection takes place. So here is a movie which shows all of that in tandem. So let's see. So this top part shows you contour plots of the magnetic fields or either the magnetic fields or the current density. And here is you can start to see the formation of islands like you have seen previously in a picture. So what's happening is the field is coming, the antiparallel fields are coming, interacting, the flux is getting expelled into the formation of these magnetic islands. So the magnetic flux gets concentrated in these islands. The reconnection keeps proceeding as such. And the rate of reconnection is given by this electric field evolution that you will see in this plot. And this plot is the distribution of the particles along the energy as I've shown you before. So you can see what's happening with that particle distribution also as push. Okay, let me restart this. Yeah. So as the reconnection proceeds, you can see there is some particle acceleration. In particular, at a later point in time, the plasmoid instability arises, which is responsible for these arising small islands, which then kind of merge with the larger islands and so on. So let me continue this. So the small islands arise and merge with the larger island, and you can see the reconnection achieves a peak over here. But as the simulation ends, you can see that the particle energy spectrum kind of acquires a tail indicative of re-acceleration. Sorry, not re-acceleration, just acceleration, and so on. So you get these high energy particles at the end of the at the end of the simulation. Right. So in this particular plot, what I want to show you is that the slope or the slope that is achieved that corresponds to how much how many high energy particles that you have in the system, it depends on this parameter theta or even sigma. I mean, basically, what you are putting here is you are varying the magnetic field strength or correspondingly the temperature of the plasma. So 0.05 corresponds to 10 to the power of 8 kind of plasma. If you go beyond 0.05, you are entering the relativistic regime. If you are below 0.05, then you are in the non-relativistic regime. Okay, so the 0.05 corresponds to this, but this thing. So and the ones that are beyond that are the relativistic, and this is all non-relativistic. Now the slope of this curve, this slope is given by this P here, and that is related to the spectral index of the luminosity spectrum, the synchrotron radiation that we saw earlier. That is given by alpha. Okay, So an alpha of 2 will lead to a P of 5. Okay, so if you want to achieve a alpha of 2, then you need to have a P of 5. So you can see kind of you do get these kind of steep spectra. But if you have an alpha of 1, then you need to get a P of about 3.
Pallavi,
And
sigma, is sigma related to plasma beta? Can you read off plasma beta from that?
So the
higher will be
plasma beta, the plasma beta is because we are requiring that initially things be in pressure balance. Okay, the plasma beta is always going to be 0.5.
Oh,
okay, to begin with.
Yeah.
But the theta is a measure of temperature, so it's kBT divided by MC square.
That's the same theta
whereas
as
sigma,
Maxwell-Ratner, right? So you start off probably with a,
yeah, that's the same theta. Yeah. So this theta will go into the distribution function. That's right. So yeah. So what I wanted to say was that basically we do seem to see the P's that we want corresponding to the alphas that are there in the observations. So this is some kind of good news that even with non-relativistic plasma, you can actually get the kind of acceleration that you desire. Now, I was going to go through a lot of estimates, but since we don't have time, I will just say that we have tried to make the estimates to understand whether this is a viable option. So how do I understand whether this is a viable option? Firstly, whether the frequency of such reconnection sites is sufficient that you can have efficient reacceleration. Okay, so we have tried to calculate how many regions can you get out of these intermittent magnetic fields, because like I told you before, fluctuation dynamo gives rise to intermittently very strong magnetic fields. So you can actually use the PDF of the fluctuation dynamo generated fields to estimate the number of these regions. Okay, and then estimate what is the distance between these individual regions, and estimate how much time it takes for an accelerated particle to go from one region to another. So we find that it is about 10 to the power of 5 years, and that is much smaller than the cooling time scale. So we are safe. Okay. The other thing that we want to estimate is what is the time scale related to the acceleration, right? That also needs to be quite small. Otherwise you are sunk. And I mean, otherwise it's not an efficient process, right? And also because these current sheets that you are, where you are accelerating are being generated due to turbulence, right? Fluctuation dynamo is a turbulent process. So then there is a finite lifetime associated with this current sheet. So you can ask whether this tau acceleration by tau lifetime is a small quantity or not. Otherwise, you cannot do this, right? So we make again an estimate. This estimate depends very much on what is the critical Lundquist number, so the Reynolds numbers in the system. So we find that this does turn out to be a very small quantity. But more importantly, what is really important is the maximum Lorentz factor, because see, the simulation is a micro physical length scale, right? Because we are looking at really length scales which are like 1,000 times, like 200 times the skin depth and so on. So these are really tiny length scales. So then the question is that, are we really capturing the large scale properties? So we are not really, because the current sheet can be much larger than what we show in the box. So if you want to capture those numbers, then you have to do some kind of an estimate. Here, what we show is the maximum Lorentz factor that you can get, that is the kinetic energy associated with the particle, will be equal to like the integration over the work done by the electric field on the particles. Okay, so that is given by this equation. So you can make again an estimate of what is this. So if you know what is the reconnection rate, that will give you this the electric field associated with this reconnection. And then you can take the dt to be the lifetime of this current sheet. And then again, you can make an estimate, and that also crucially depends on this S crit by S, where S critical is the critical Lundquist number associated or Reynolds number associated with the magnetic reconnection or the plasmoid instability to take place. Again, we make an estimate and we get like 10 to the power of 3 kind of thing, but that is sensitively dependent on what is the Lundquist number of the plasma. And that is like, if you make a Spitzer estimate, that is like some 10 to the power of 27, really crazily high number. Okay, and we expect that this number should be lower. And if this number is lower, then we can actually achieve even larger gamma max. So that would correspond to what we see observationally, etc. So we think we have hit upon a very nice possibility, which especially because in the center of galaxy cluster where you may not have shocks, etc., you can still have fluctuation dynamo giving rise to these intermittently strong magnetic fields driving particle reacceleration. And with that, I will end my talk. Summary is that magnetic fields are ubiquitous in the universe. Astrophysics really needs to account for this, and not only needs, it will actually be fruitful to account for this. And the new frontiers, I mean, frontiers don't take it in some big sense. It's like in the ICTS sense that we are exploring at ICTS is 3D reconnection, dynamo in collapsing background, GRMHT simulation, some of these are the new things that we are doing. Of course, particle acceleration in galaxy clusters, with which we can, using magnetic reconnection, we can try to explain the non-thermal emission that we see. Okay, with that, I will end the talk. And just to kind of bring back all the characters of this play. Yeah, so these are all the students and postdocs working with me. Thanks.